This is actually stealing Chang Wei Tan's spotlight because unfortunately he's ill and unable to be here. This is a slide I first saw several minutes ago. It's also a companion slide to the slide that I'm going to talk to in about 20 minutes' time, I think. So I'll remember what I say now because it'll be background for what I say then. So time series are a very frequent form of data. They capture the evolution of a process over time. You'll be familiar with time series. An important operation on any type of data is being able to assess similarity, so how like two things are. This is one of the underlying principles of many tasks such as clustering, classification. The classic way of doing, of assessing similarity is dynamic time warping, developed in the 70s. Dynamic time warping essentially allows you to line up the series but to distort the alignment so that you're not assuming that points are directly aligned one after the other, but allow that two different processes might evolve at different speeds, or you might have slightly different starting points at which you started recording them or whatever. However, if you allow that to happen in an unconstrained way, then it can be too permissive, as you will see in 20 minutes or so time when I talk about our new approach to doing this. The classic approach to dealing with that is to use windows, which limit the amount of warping which is allowed. But the problem then is that you need to work out what window to use. So if you come to our poster, we'll tell you our super fast way of doing that. If you see the bottom right figure, the classic way of doing it over the benchmark UCR time series classification repository takes 1,100 hours. There's a fast way of calculating DTW and utilising lower bounding, which is a way of speeding things up at about halves the time, exploiting our new very fast computation of DTW, gets down to under 200 hours. If you do all of our optimisations, we can take it down to under 4 hours. I think I've run out of time.
Yep. So the stability of a protein is one of the most important properties because even a single mutation can change the protein structure and stability. In the above figure, we can see that one of the residues, the tryptophan, is changing to glycine at 168th position in one of the protein and changing the structure. The residue is highlighted in the magenta color. Mutations may affect the binding of the protein with other molecules, can disturb the formation of complexes, and even it can lead to drug resistance. There are various predictors in the literature developed due to this reason. Many of them are the structure-based. There are only seven in the sequence-based category. Because the structure-based predictors, they have a higher performance than the sequence-based predictors. So in this study, here we are developing an AlphaFold 2 aware sequence-based predictor for the stability change prediction upon mutation. So here we take the protein sequence as an input and the mutation info. Then we extract multiple features. One of the key features that we are using is the predictor structural features. The protein structure is predicted using the AlphaFold 2 program. And within 8 angstrom of the mutation site, we are extracting multiple features using the Permaco4 feature labeling. Then the feature vector is passed to the ensemble model, and the final delta G value, the stability change is predicted. To know more about this work, let's chat at the poster.
Thanks very much. Hi, so yeah, this work on relative flatness and generalization actually ties very well into Din's talk. So Din talked especially about this adversarial robustness, but you can also have the same problem from the view of the classical statistical learning theory. So you don't consider adversarial examples, but just generally the question, even if you have samples from the same distribution, how robust is your generalization? And so the issue with the classical learning theory, so I see a couple of students from my unit. So we talked about the bias variance trade-off, and usually you have this picture that the training error, the test error goes down when you add more parameters to the model. Eventually it will go up because the variance is increasing and you get into this overfitting regime. But then what people discovered in the deep learning regime, when you actually go to models that can completely interpolate, you add more and more parameters, eventually error goes down again. So it's this double descent phenomenon. And it's not well understood in the theory, actually, still, why that happens. I think work like Din's is probably contributing to that. Another hypothesis, another kind of view is this flatness view. The idea is that if you look at the risk surface in parameter space, that the backpropagation actually tends to find flat minima in the sense of the second derivative. But the problem with that hypothesis, a long-standing hypothesis since early 90s or so, is that this measure is actually not invariant to reparameterization, but the generalization is. So you see, theoretically, it cannot quite map. And so this work is led by a former postdoc, Michael Kamp, and his colleague in Germany, investigates when actually, or how do we have to modify the flatness measure, and under what conditions can flatness indeed imply generalization. That's it. More at the poster.
Hi, I want to introduce our NIPS 2022 works, which is rethinking and scaling up graph contrast learning, an extremely efficient approach. So in short, basically we have found out this technical defect in a very famous graph contrast learning method, which is DGI. And we fixed that technical defect and come up with a really efficient approach called GGD. And for example, on a really famous large-scale data set, OGBN archive, we are 10,000 times faster than the fastest baseline while consuming 70% less memory. So the idea is really simple, because for contrast learning, we know we want to maximize the similarity between the positive pairs and minimizing the similarity between the negative pairs. But what we do is we use group discrimination instead. So it is a binary classification task. So the task you need to do, or the only thing that model need to learn is to discriminate a node that is generated with the correct graph structure or the incorrect graph structure. So it is a really, really simple method. And also it is scalable because we have successfully run it on a billion scale network. And I found it is quite difficult for me to do that due to our, based on our available resource in the department and the faculty. So I would kindly request or suggest that we probably need to upgrade our hardware and buy more GPUs. Thank you.
Hello everyone, my name is Chung Le. I'm glad to present our work published at ICML this year. This work was led by our PhD student Long Vương. In this work, we aim to learn deep discrete representations. The seminal work is VQVE. Here, the pipeline of VQVE. We start from images. We employ encoder to map images to latent code. And we further split latent code into many equal latent chunks. We maintain and learn a set of code words, which we subsequently quantize a latent chunk to their closest code word and gather them together, fit into the decoder to reconstruct original images. However, VQVE and its further work relies on K-mean to learn the code words. Hence, they suffer from some limitation. First, the conversions of the trainings totally depend on the initialization of the code word. Second, VQVE cannot utilize the code word efficiently. Our motivation is from the clustering viewpoint of water style distance, and based on this observation, we develop our theory. Basically, we start from a generative viewpoint of learning discrete computation. Our work is the first work that propose and study this viewpoint. We develop a solid theory to turn this one to trainable objective function and connect this to controlling viewpoint of optimal sandbox theory. Finally, we conducted experiment on real-world data set to show that our approach really outperform the SOTA baseline in all measure of interest. If you are curious about our work, please come to our poster.